Some complex circuits cannot be simplified using series and parallel rules. For this, we need a more powerful tool, Kirchhoff's rules. To analyze complex network like this one with multiple loops and powerful sources, we use a technique developed by Kirchhoff. There are two rules. The junction rule, based on conservation of charges, states that the sum of the currents entering any junction must equal to the sum of currents leaving it. The loop rule, based on conservation of energy, states that the sum of potential difference around any closed circuit loop must be zero. A junction is any point where three or more conductors meet. The junction rule says the total current into the junction must equal to the total current out of it. There is a direct analog to water flow in pipes. If we have a junction in water pipe, the water current goes into the junction has to equal to the water current goes out. Same apply to the electric current as charges are conserved. A loop is any closed conducting path. The loop rule says that if you sum all the voltage gains and drops around any closed loop, the total sum will be zero. This is a statement that the electrostatic force is conservative. This analog helps visualizing the loop rule. Think of potential as elevation. A battery is like a pump, raising the potential. A resistor is like downhill slope, where potential is lost. After one complete loop, you must return to your starting elevation. Here are the sign conventions for applying the loop rule. Moving across a battery from negative to positive is a potential gain. So we have a plus E. Moving across a battery from positive to negative is a potential drop with negative epsilon. Moving across a resistor in the same direction as a current. If the current is this way and if we move in the same way, is a potential drop of negative IR. Moving across a resistor against the direction of current. In this example, current this way, loop this way, is a potential gain of plus I times R. The junction rule is a direct statement of the conservation of charge. In this diagram, the current I1 flows in must equal to the sum of current I2 and I3 flowing out. To solve a circuit, we must first assign symbols and a direction to the currents in every branch. Don't worry if you choose a direction of current that is actually opposite to the current flow in real life. The answer will just come out negative. Then choose a direction of loops and then we travel around the loop and apply the loop rule, recording voltage drop and rise as we go. So let's get ourselves familiar with this by a very quick example. This is a classic two-loop circuit. Require Kirchhoff's rule to solve. So we have the circuit given, which have more than one battery, and the two batteries are in different branches. But this is a not so bad problem. We have a junction here, and we have one current that goes in the junction, which is 6N. And we should have two current that goes out. This current that goes this branch will cross the resistor R. we can just name those resistors and currents. This one is R. Let's call this one R2 and I2. So I2 is 4. Let's call this one I3. This resistor R3. So this current I3. So we should have I3 goes in this junction. Should equals to, call this one I1. Current going through R2 is I2. So for this junction, we have I3 goes in, I1 and I2 goes out, and I3 is 6. I1 we don't know, need to solve, and I2 is 4. So we can quickly solve it and find out the current going through R is 2 amperes. So this is answer for part A. Part B, we need to find out what's this resistance. Now we already know the current going through it is I1 equals 2 amperes. So we can choose, let's just choose a loop like this. And our loop goes counterclockwise. Then start from the battery. Okay, we should, from negative end to positive end the battery, we have a potential gain of 28 volt. Keep moving. And then we meet the 3 ohms resistor. And the loop is in this direction, current is in this direction. Use the resistor. Potential rule is a potential drop. I times R. Keep moving. And then we have this R. Current goes this way. So it's a potential drop again. I is 2 here. R is, we don't know, right? But the loop has to sum up to 0. Okay. So we build an equation which only has R, so we can quickly solve. This is 28 subtract 18 is 10 minus 2R equals 0. So R equals 5 omega. Next, we need to solve this unknown EMF. We can choose the lower loop, also choose it as counterclockwise. Let's start from here and go to here first. This start our loop. So this is another potential increase because we move from negative end to positive end of the battery. Keep moving. We see this 3 omega resistor, and the loop is in the same direction of current, so it's a potential drop. And we need to go back to this point. So we see this 6 omega. The loop is in this direction. Loop is in this direction. Current is in this direction. So it's a potential drop again. Current is 4. Resistor is 6. Should add up to 0 because we come back to where we start. So epsilon equals 3 times 6 plus 4 times 6, 18 plus 24. 42 volt. So this is answer for part C.